Hi, and welcome to this short video about a note about elevators and the normal force. I'm specifically making this video right now for my class this year, where we just finished doing an exploration about the forces on an elevator, and I'll be away for a few days, and there is one thing that I thought would be very important to notice. Here I've drawn a person in an elevator, and if we think about the person as what we're going to draw our force diagram for, well, if it's going at a constant velocity, then those forces are going to be balanced, and there are only two forces. There's the force of gravity downwards, and there's the normal force of the floor of the elevator pushing up on them, and if it's at constant velocity, the forces are balanced. Now, what about the case where there is acceleration? And how about if they're accelerating up? Well, then the force of gravity is still the same force of gravity as before, so I'll put that single equality mark, but now the normal force is actually larger. So just as a reminder for terminology, when we talk about someone's weight, really that means force of gravity. If we're talking about someone's feeling of weightiness, so when you're accelerating upwards, you actually kind of feel heavier, that is the normal force. So once again, weight is force of gravity, and this feeling of heaviness is the normal force. Now, physicists often, we don't like this word feeling of heaviness, so we've actually invented another term. We've called this the apparent weight. So we can say an object's apparent weight, which is kind of like how heavy if you are the object, kind of how heavy you feel, that's another term for the normal force. It's actually surprisingly useful. So for example, if a lot of people have this conception that there is no gravity in space, I'm here to tell you that this is not true. That might be a surprise for you. So if we think, for example, what is the definition here? I'll just start. If I talk about what is space, most of the time we're going to say space. We've got an international definition. We say at least 100 kilometers plus away from the surface of the Earth. Now the Earth is 6,000, has a radius of about 6,000 kilometers. So if I was to, do a little arc of the Earth, and remember, like we'd have to go that way 6,000 kilometers to get to the center. 100 kilometers might be like right about here when we think about how large something is. So if at the surface of the Earth, our force of gravity is approximately 9.8 newtons for every kilogram times your mass. Really, if you're just going from here to here, it's hardly a distance at all. It's going to be slightly less than 9.8, but it's going to be very similar. So if you were in outer space, right at this spot here, and I was to say, what are all the forces acting on you? I'll just maybe draw it over here. Definitely, you're going to have a force of gravity acting on you. Do you have a normal force? No, you're not on a surface, right? So if you're there, you're going to actually be accelerating downwards, and unless you've got some surface that's pushing on you, like maybe a rocket ship that has thrusting right now, but you're going to have no normal force. So your apparent weight, you're going to feel weightless because your normal force is zero. So you see how it's kind of useful. So we can say, oh, in space, there is gravity. It's very hard to get to a place where there's no gravitational forces on you. If you're just 100 kilometers away, your force of gravity is going to be very close to what it is at the surface of the Earth. The difference is often when you're in space, there's no normal force, in which case you feel weightless. If you just jumped out of an airplane and were falling for a little while before really air resistance hits you, you're going to have that same force diagram, and you're going to feel weightless as well. Okay, so that's all I wanted to add in there, is this concept of that another name for normal force is apparent weight, just like weight is the force of gravity. Okay, thank you.